10.3, apply properties of chords. Now remember a chord is a segment of a circle whose endpoints are on the circle. Alrighty. The question here, how can we tell if two chords are congruent? A couple of things here. First of all, congruent chords are chords of the same length. Okay, remember chords are segments, and segments are congruent if they have the same length. Bisecting arcs, again, all sorts of things can bisect arcs. It could be a point, it could be a ray, it could be a line, it could be a segment. So we should say that any ray, line, or segment that contains the common endpoint of congruent adjacent arcs. Alrighty. So what this would look like is if I had a overall arc here and I had a point in the middle such that this measure was the same as this measure, then anything that would contain that point would be considered a bisecting of an arc. Okay. And a perpendicular bisector of a chord, we'll just sketch this here. So here's the center of the circle, here's my chord. If we go ahead and do a perpendicular bisector, meaning that's congruent to each other and we have a right angle, that's what the perpendicular bisector of a chord. And notice one thing here, that the center point is covered by that perpendicular bisector. So we'll keep that in mind. A1. Let's go ahead here. They want us initially here to have two congruent chords with a common point B. So here's A, B, and D here. And D. And all we'd have to do is say this is congruent to that. Okay. Semicircle GHI. Remember, a semicircle is half of a circle. So I'm going to go ahead here. Go ahead and drop in what looks to be a diameter, G, I, and H. Okay. Diameter HG, which I guess I have here, so I can darken this in now. And chord ED is congruent to chord GH. So if here's D, I'm going to go ahead and change colors here. And if I've got to go ED, and here's where E has to be. Since chord GH is a diameter, then chord ED also has to be a diameter. Continuing here, theorem 10.3. In the same circle, or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Now remember, an if and only if is a very strong statement called a biconditional statement. Now keeping that in mind here, looks like I have a chord, and a chord. These other two are radii. They are congruent. So which means their arc measure is congruent. So now we know all the way around the circle is 360 degrees. So 3y plus 72 equals 360 degrees. Let's just subtract 72 over, and we get 3y equals 288. And divide by 3, and we get y equals 96. So 96 degrees, 96 degrees, 96 degrees are what y has to be. A3, continuing here, same type of idea here. They want us to find this z when I've got congruent chords here and here. So that means if that's 128, this is 128 degrees. And like our similar problem here, we know that 4 of these have to be 360 degrees. So let's go ahead here. We could say 128 plus 128 plus 20 plus z equals 360. Now let's condense that left side there. And looks like we got 256, 276, 276. Looks like 276 plus z equals 360. Thus z would have to be 84 degrees. Now moving on to A4, a similar type problem here. It looks like I have two chords that share an endpoint, so this is congruent to that, which means this measure is congruent to that measure. Okay. Now they're telling us that BC is 110 degrees, which means this is 110 degrees from measure, and they want us to find this guy right here. So again, question mark will equal 360 minus 110 minus 110. So 360 minus 220 should give us 140 degrees. Continuing here, some theorems here. So a little run on theorems. If one chord is a perpendicular bisector of another chord, then the first chord is So here's a situation. If I've got, here's a chord. If I've got a perpendicular bisector, and it's got endpoints, this, again, since it includes the center, then it's got to be a diameter. So a chord that includes the center point is defined as a diameter. Theorem 10.5, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord, the chord and its arc. So if we go ahead here, if I have a chord, and if I've got a diameter that's perpendicular, that will then mean that this is congruent to that, and that this measure is congruent to that measure. That's what it's leading to. 10.6, in the same circle are congruent circles. Two chords are congruent. If and only if they are, okay, let's take a look here. Here's my center. Here's a chord. And let's say we got here's a chord. If these chords are congruent, then I would say that this distance must be the same as this distance. And that's what we call equidistant. So equidistant from the center of the circle. All right. So now with these few additional theorems here, let's go ahead and see if we can answer these last few problems here. This goes back to our previous type problem here. Since this is congruent to this, then this has to be 147 degrees, and this would be 360 minus, and this is what we're looking for, MN, 360 minus 147 minus 147. And that ends up being 66 degrees. Over here, it looks like we have equidistant and perpendicular. So that means this chord has to be congruent to this chord. So 3x plus, 3x equals x plus 17. Subtract the x over, divide by 2, and we do get 8.5 for our answer. Last one here, find the perimeter of this pentagon, 5 sides pentagon, if the following is true. AB and BB are 6. So if this is 6, these are congruent because of the perpendicular. So this has to be 3 and 3. BD, this is also 6. OP is 4. So OP, I got 4 right here. And CD is 8. So that means 4 here and 4 here because of the perpendicular. And then OQ is 3. So it looks like I need to add up these 5 lengths to go ahead and get my perimeter. And that's going to be 3 plus 4 plus 3 plus 4 plus 6. And to me that looks like 20. In this case we had centimeters. That concludes lesson 10.3's notes.